Good morning and welcome to today's lecture on big data. I hope you enjoyed the last few days and the Easter holidays. And today we're back to big data. As usual, there will be a quick revision of what we did in the last lecture. And today we have a double lecture to speed up with the content, so you'll have a little bit more time also for the seminars later on. Last week, we started with the concept of a thread pool, and we saw what that concept is. We can easily use it to run multiple tasks at the same time, like, for example, downloading web pages, because most of the time our thread is actually waiting, for example, because of latencies in the network. So we don't just want to download them sequentially, but rather in parallel. And the thread pool is one way how we can do this very easily. We saw also a couple of experiments, and then we had the idea that we have one very complex task and that takes long. For example, this was just simulated with a very large countdown, but could represent some much more complex function that takes long to run. And we have in our modern CPUs multiple cores, but we're only using with a single thread one core. And we wondered how can we actually split that task among two threads. We wondered what kind of speed up that would eventually lead to, but it didn't really lead to any speed up in Python, which we noticed. And that has to do with the global interpreter lock, which eventually enforces Python to be single-threaded. There are various reasons for this global interpreter lock. First of all, it looks like a major limitation, which it is, but it's more. It also provides us with various advantages because we don't run into leaked memory or deadlocks easily. And there are a couple of reasons why the global interpreter lock was introduced in the early days, because it allowed to build thread-safe Python applications easy and to integrate lots of lots of legacy C libraries which were not thread-safe at that moment. The global interpreter lock, however, is a limitation, leads to effectively single-threaded applications. So one way to go around that is to do multi-processing, because multiple processes can obviously be done. Then we don't have shared memory. Multiple processes, however, lead to some extra work in the operating system, and it's more expensive to create a process. Now we're wondering if the global interpreter lock can be removed, and this was debated for a long time. And some Python implementations don't have a global interpreter lock, and in Python, at least in CPython, in this year's discussion, there has been some movement slowly replacing the global interpreter lock, and we saw that last week. We also saw how much you actually need in practice of all of this, especially when you do data science. A lot of these multi-threaded features are under the hood available for you, which makes it far easier for you. Today in the lecture, we'll see a little bit more of other approaches, what others have been doing in order to use parallelism most easily. Then we started with the big architectures chapter. We've talked about, first of all, a revision of database management systems, which is important for today's lecture. We looked at indexes, we looked at database normalization, and a very important set of guarantees that we call ACID, atomicity, consistency, isolation, and durability. I also presented you this SQL murder mystery, which is for you if you want to do a revision of your SQL skills or if you want to improve them. Don't know if you had some time to look at it, but if you had, probably it was a lot of fun. We also looked at your reality that you're typically dealing with. You're running some machine learning experiment on your local computer, but in reality, you need much more space, you need much more computing power, much more RAM, and you also want to, if you build a service, you want it to run reliably so that it's not just gone if your local computer crashes. We looked at distributed systems, and then we talked about the cloud, its pros and cons. I think, first of all, cloud services are something very important because it allows you to scale, but they come with some new risks that we also discussed last week. And eventually, at least at a certain size of your company, you need to pick a hybrid approach because you need some basis that probably runs on site that you have full control over. And you cannot just be put out of business because your cloud provider tries to delete you, but the cloud can be very helpful for scaling. Today, we will continue this chapter on big data architectures. And as we saw in the last lecture, doing parallelization is tricky. We saw why, because you can run into all these issues like deadlocks and leaked memory. And obviously, you have now these libraries at hand that does a lot of parallelization under the hood. But first of all, they need to be built, and someone still needs to know about how to do parallelization. And Google in the early days obviously started to process big data sets or data sets that were considered big at that time. And even though they hired lots of smart people, they noticed that a lot of their software engineers struggled building highly parallel code, because when you build parallel code, you have all these issues we discussed before. And they proposed a solution to that they called MapReduce. And we will now briefly look at the MapReduce paper and see what MapReduce is about. MapReduce is essentially an abstraction for parallelization. So Google introduced that internally, and they trained their software engineers in rethinking algorithms in terms of two stages: map and reduce, and write the corresponding functions, and then put them in the MapReduce system that was provided by Google at that time, and then the parallelization was taken care of. So you had to rethink your algorithm problem in terms of mapping and reducing, and then the actual parallelization was done for you. And they wrote a paper about that, and we'll discuss this paper now very briefly, or I walk you through the paper. Obviously, you're expected to read the full paper to get a better understanding of that idea. So MapReduce will directly look at this figure and see what it's about. So you have two phases. You have a mapping phase and a reducing phase. And when you have a very large input that would take just a very long time to process in a single threaded application, you can try to split the input into various parts. And then these parts are processed in the mapping phase on different worker nodes. And that's a parallelization you can do very easy. You just have a large data set and you split it into various parts, and then each worker processes one or multiple of these splits. And then in a reducing phase, those are eventually, those results are actually aggregated or combined on worker nodes. In between, you may store the results on for example, on a disk, and then on the worker node, you're aggregating or combining the results from the worker nodes from the map phase, and then you create your outputs. Maybe one worker in the reduce phase or multiple, but then each worker generates an output file, and maybe further you need to combine these output files or not. And because this looks highly abstract, we will be looking at an example, because there are plenty of examples in here, what you can use this for. For example, just looking for the example where, so there's lots of code and experiments in here that you're most welcome to read. And there was one example, probably it's written, so I'll briefly visualize it on my own, and then we can develop it step by step. I'm just switching to my iPad, and then we will develop this on our own and not just go through the paper of Google. So you should be seeing the slides now. Imagine we have a text. So this would be our input. Very large text file. And it contains multiple words. So word 1, word 2, word 3, and so forth, up to word n-1 and word n. And this file could be extremely long, so n could be billions or trillions of words. And what I want to calculate is a statistics, which is a count per word. So our result eventually would be something like this. We count unique words. The result would be unique word 1 appears k many times, or k1 many times. Unique word 2 appears k2 many times, and so forth. We have n, or say m, unique words, and we have the count km. And we can also look at an example. For example, we can, just to highlight this more clearly, we have the input would be some string which have 4 words: hello world, this world, for example, and the result would be hello appears once, world appears twice, and this appears once. So this would be the result that we want to compute. And obviously, in reality, the input is much longer. And for that, we can try to use MapReduce, because we have this super long text file. We could just split this text file. Visualize here, MapReduce. We have, this is the first chunk, second chunk, and so forth. We could, for example, say we split this into 3 parts, and then we have our workers. Input gets split into 3 parts. Then we have 3 workers: worker 1, worker 2, worker 3. And each of these workers does what we have just visualized up here. Each worker goes through its input part, input 1, input 2, input 3, and calculates this dictionary, because eventually the result is a dictionary where we have a key, which is the string, and the count is the value. It calculates, or each worker calculates this dictionary and counts how often each unique word appears. So this is the map phase, and then the reduce phase. We would say we just have 1 worker, and so this is, say, worker 4. And then in this reduce phase, we just combine these 3 dictionaries and then have our result dictionary and save it. And the beauty of this MapReduce approach is we don't need to worry about parallelization. All we need to do is we need to write code for these mapping and reducing phase, Mapping would mean go through an input, calculate the dictionary, count these unique words, and then in the reducing, we would just process multiple of these dictionaries and combine it into one big dictionary, and we're done. And that's all the code we need to write. And then we let the MapReduce system do the rest for us, which is splitting the input, running these workers, managing how to create threads and how to do this in a thread-safe way. And then once the map phase has completed, put the results into the worker of the reduce phase, and we're done. So we don't need to worry about parallelization. And this approach from Google actually became super popular within a short time, because within Google, all they needed to do was to retrain their software engineers to rethink algorithms in terms of a mapping and a reducing phase. And once you were able to rethink an algorithm in these two phases, you just needed to write the corresponding code for mapping and reducing, and eventually the MapReduce system handled the rest for you, and you didn't need to worry about parallelization on your own. This paper is 13 pages. It contains more examples. Also contains a couple of experiments and comparison of running time, a couple of implementation notes, what they noticed when they implemented the system. So read the paper and see this. This paper was from about 20 years ago. Obviously, MapReduce has evolved. MapReduce was the basis, for example, of Apache Hadoop. Hadoop was sort of an open source clone of what was proposed in that paper. And then new approaches came up that are also open source, like Apache Spark and Flink. They are somewhat inspired by the original Hadoop and the MapReduce phase. However, they have done lots of variations and extensions in order to speed this further up with a couple of guarantees that have changed. But overall, I would say this MapReduce paper is probably one of the most important papers in the last 50 years that was ever published in computer science, because it really led to a revolution in how to process very large amounts of data, and many new concepts have followed from that paper. Feel free to look up Apache Hadoop or Apache Spark in case you haven't used them yet. Use them and see how this can be used concretely. This year in the seminar presentations, we are working, or you're presenting book chapters from this book on design patterns in machine learning. In some of the past years, we also discussed in the seminar presentations tools like Hadoop, Spark, and others. But this year, we're focusing again on the machine learning design patterns. But in case you want to try this out, just install Hadoop, Spark, or some other variation thereof, like Flink, whatever, and see how it works. I don't know, has any one of you ever used Hadoop, Spark, Flink, or something like this? If you have, maybe just send me a thumbs up or thumbs down here in the chat, so I see if anyone has already used this or not. So didn't get any reactions from your side yet, but if you have used anything like this, maybe let us know. Now we will wonder about what is actually possible in terms of distributed systems and what is not possible. Maybe let's think about the following. When we have a distributed system, we have multiple nodes, and what we want is that these nodes are consistent, because we need multiple nodes in our distributed system, maybe just to handle lots of load that we're getting from our customers, like say a social network like Facebook. We have multiple nodes and we want to process the customer or the queries of the users very quickly. And we all want them to get exactly the same state of the social network. So we want our nodes that are distributed around the world, we want them to be consistent. We also want high availability, so we don't want our users to actually wait. So availability is important. That's why we maybe have multiple nodes. But because it's a distributed system, some of the messages in the system among the nodes, they may get lost. And we also want to address that. And if our system continues to operate despite some of these messages between the nodes get lost, we talk about partition tolerance. And now, in an ideal world, you would want a distributed system that can address all three at the same time. We want the distributed system to be highly available. We want it to be consistent, but we still want it to work if messages between the nodes get lost. And it was proven about 25 to 30 years ago that that is impossible. In a distributed system, you can only have both, or you can only have two of those three guarantees at a time. So you can only say, if you have partition tolerance, you can only pick between consistency and availability. You cannot have all three at a time. This is impossible. And now you wonder, which ones should you pick? And we had looked at relational databases last week, and I mentioned ACID, the set of guarantees, which was atomicity, consistency, isolation, and durability. And you can have very large relational database management systems, and you can have them distributed among multiple nodes. And what they pick is, they pick consistency and partition tolerance. Partition tolerance is crucial, and then they can only pick one of those other two, and they pick consistency. Because relational database management systems make very strong guarantees with ACID, and then consistency is more important than availability. Social networks, they often make a different choice. They favor availability. And I want to ask you if you have maybe noticed something like, say, you use Facebook or LinkedIn, and maybe you make a post, and maybe you can see your post already, but maybe your friends cannot yet, or you refresh and maybe your post is not visible anymore just after you had posted and you saw it. And if you refresh again, maybe it's there, or it's the same with a comment or a like or a message in a social network, that when you refresh, maybe you're not getting what you just saw before, but maybe the post or message is there or not. And over time, if you keep refreshing, it's eventually there. Have you ever noticed something like this in a social network? Maybe send me a reaction if you have seen something like this. Sometimes appears on LinkedIn or Facebook. We got some reactions that you have seen that. And that has to do with the guarantees made by such social networks. I've mentioned ACID and the CAP theorem. Relational database management systems, they definitely choose consistency over availability. But there is a totally different world of distributed systems and database management systems, which we sometimes call NoSQL. NoSQL is a term that came up maybe 15 to 20 years ago, maybe in the early 21st century, when all these Web 2.0 companies came up, and then this term NoSQL was coined. NoSQL is actually a sort of strange term from my perspective, because you have these new database approaches, and they're called NoSQL, yet some of them, they actually use SQL or some query language that is inspired by SQL. So I personally don't like the term NoSQL too much. I would maybe call this sometimes not only SQL, which emphasizes that they may support query languages like SQL, but it actually refers to a much more diverse set of architectures that is under the hood. However, such databases have actually existed since the late 1960s. So they're actually nothing fundamentally new. However, they have become more popular in order to handle big data in the last 15 years or something like this. These NoSQL systems, as I said, it's a huge set and a very diverse set of approaches and architectures. But what you often see around them is that they don't use ACID as a set of guarantees, but a different set of guarantees that is called BASE. And BASE stands for basically available, soft state, and eventually consistent. They use the CAP theorem in a different way. So a soft state means you have a state, but it's not maybe fully consistent among the nodes. Rather, it's soft, not always consistent. The states will eventually become consistent as time passes, but the system is basically available, which means as much available as possible, using all the nodes of a cluster, and you have basic reading and writing operations available as much as possible, but they don't come with any kind of consistency guarantees. So this is something you don't want to be using in a bank in order to manage your bank account. But in terms, for example, of social networks, that's really good, because when you open the social network, you want to see something, and probably something that is relatively consistent and relative up to date. But if it's a few seconds or a minute or two out of date, but you get the result quicker, probably that doesn't matter. So the system will be basically available as much as possible. You have a soft state, and over time, hopefully very, very quickly, the system will become eventually consistent. If such a social network like Facebook or LinkedIn purely relied on ACID, it would probably be totally consistent among all the different nodes spread all over the world, but the system would be extremely slow and probably unusable, because you have a lot of reads and writes at the same time. And if you send a message, it just doesn't matter if the other one receives it after 1 second or 5 seconds, based where he or she is all around the world. Or if you post something and you immediately refresh and you see your post or not, or if others in the social network see it immediately or after half a minute, probably that's not too important, as long as the system is basically available. So you can post and read, and it will be eventually consistent. And that's, as I said, a consequence of the CAP theorem. And the CAP theorem is proven mathematically, and you're unable to provide all of these 3 guarantees at a time. However, there's also a lot of, say, misunderstandings around the CAP theorem. So the CAP theorem obviously implies, in the presence of network partition, you have to choose between consistency and availability. But when there are no network failures, then you can have availability and consistency at the same time. And you don't really have to abandon one of those 3 guarantees at all times. Rather, if your network works relatively reliable, probably most of the time, you can have consistency and availability at hand. When there are more losses on the network, obviously, then it gets more tricky. But if there are no network failures or extremely little, probably you will not feel the impact. However, if there are a lot of network failures, which happens probably in a very large distributed system spread all over the world, where maybe some of the network connections aren't that reliable, then you would feel more impact because of the CAP theorem. As I said, the relational database management systems, they choose consistency over availability. And then you have other systems, especially used around social networks, whatever, that would be favoring availability. When it comes to you, when you build a distributed system, it's important you check with your customers which requirements they have. Would you favor consistency? Would you favor availability? That really depends on your use case. if you are in, say, banking, probably consistency is more important. In social networks, availability, and some trade-offs need to be made. I said that next month we will have a guest lecture by one of my friends who works at Google. As far as I remember, his guest lecture will be how they address the CAP theorem at Google, but you'll see more next month when we have the guest lecture. I'll inform you in advance before it takes place. And I already look very much forward to the guest lecture next month. So this is the CAP theorem, where we saw what its limitations on distributed systems are. Now that we have distributed systems discussed, you should also read the MapReduce paper, maybe take a little bit a look into Hadoop, Spark, Flink, and see how they work and how you can use them. And eventually Hadoop was inspired by this original MapReduce paper. Now we'll discuss a different topic of how you can speed up computations in the machine learning world. Nowadays, GPUs, graphics processor units, are extremely popular in order to train neural networks. We'll discuss this now a little bit, and we see what GPUs are useful for, what they are maybe not useful for, and how all of this will develop in the coming years. If you use a modern GPU, it will have lots of cores. A few years ago, there were very popular GPUs like the K80 from Tesla. They had up to like 5,000 cores. Nowadays, with the latest kind of GPUs from NVIDIA, for example, a V100 or something like this, they have less cores, around, I think, 640 cores. They don't use that high number of extremely small cores anymore, but we'll be discussing this now. And I want to know from you, who of you has used a GPU so far for training a neural network? Maybe thumbs up or thumbs down if you have done this already. Oh, some of you have done this. If you want to use a GPU, in the past, GPUs were popular for playing video games, for rendering. And most people just use them as end users. But over the years, it has been noticed that they are actually very helpful for training neural networks, plus other machine learning models. If you want to use a GPU in your code, you need to learn how to write such low-level code. For NVIDIA, this would be CUDA, but there are also competitors of NVIDIA. So you need to learn how to write code for a GPU. Or that's what it looked like in the past. Nowadays, we can use libraries like TensorFlow, Keras, and others. They take care of that for you. All you need to do is you need to write high-level code, for example, in Python, and this gets mapped for you on a GPU. So you don't need to worry about the GPU code that much anymore. If you're an expert in CUDA programming, probably that's helpful because the automatic mapping will not be as great as if you're an expert, but probably most of us don't have time to become an expert in CUDA or some other low-level environment from other GPU vendors. So we can take advantage of GPUs without knowing how to code for GPUs. And I think this is something that is overall very helpful. So why are GPUs that successful or that important for training neural networks? Eventually, a neural network and its training, as well as its forward propagation for predicting, can be described in terms of linear algebra operations very well. For example, in terms of matrix multiplications to a large extent. Now, matrix multiplications have the great advantage that they can be parallelized extremely well, because in a matrix multiplication, all you are doing are very simple operations. You want to multiply individual elements, you want to sum products together, and so forth. So actually, you don't need very complex operations. Rather, you just need very simple operations, and you want them to be highly parallel. And that's exactly what GPUs are doing, because GPUs in video games, what they're doing is we're rendering, and rendering or operations in computer games for the visualization, it's largely just linear algebra, adding matrices, multiplying matrices, and so forth. And that was understood many decades ago that can be parallelized with a GPU. And then it was understood, well, if you express all your operations and training a neural network in terms of matrix operations or linear algebra operations, in particular matrix operations, then you can map this to a GPU and massively speed up the training of your neural networks. This is something that started to become popular maybe 12 to 13 years ago. And nowadays, everyone is doing it because it just gives you these massive speedups. But we still need CPUs. And I want to tell you, some 10 years ago or something, someone told me something. I'm not saying who, but I have written down this quote here. And this person said that CPUs have no future. The future belongs to GPUs. Personally, there is some truth to that statement, but I think it's highly exaggerated, and it depends on what kind of tasks you're actually talking about. So let's compare CPUs and GPUs a little bit. CPUs are actually extremely useful, and they will not disappear because of GPUs. GPUs, they will have their stake, especially for certain tasks, but I don't think CPUs will disappear in the foreseeable future, because CPUs, they can execute very simple, but also very complex instructions. They can do more than just multiplications or additions. They also have a very complex set of instructions. The advantage with CPUs is that they are very easy to program. You can easily pick up how to write C, C++, and then you can use other languages like Python, whatever, which is even easier. But for more from a low-level perspective, like C, it's very easy to learn. So writing code for a CPU is straightforward. And the great news is, even if you write very inefficient code, a modern CPU can help you to massively speed up your inefficient code. For example, there's branch prediction. Branch prediction is something extremely important, because a branch would be if you have an if-else in your code. And what a CPU is actually trying is, if there's a statement which takes a little bit of time to execute on a CPU, the CPU will try to look ahead and already execute some of the following instructions if possible, if they are not dependent on your current current instruction, which takes long. That's something we call out-of-order execution. So if you try to write your code, say in C, and you compile it into assembly code, your CPU will not necessarily execute it that order as it's written in your assembly code. Rather, it does out-of-order execution and try to already look ahead and pre-execute some of the following instructions if one instruction is slow. But then you may have an if-else in there. Or in assembly, this would be some jump, that you jump around in the code. And then looking ahead and doing out-of-order execution is tricky, because what may happen is you may look ahead in the if part, but then your other instruction that is slow is actually executed, and then it turns out that you have taken the wrong route in this if-else. So you would need to unroll some of the computations you have done. So in order to avoid this as often as possible, there is branch prediction. So your CPU tries to guess well which of the conditions will actually be true, and then it will look ahead. It may still be wrong, and if it was wrong, yes, it may have to undo some of the operations. But with branch prediction, this doesn't happen that often anymore. So your CPU can actually, in the combination of out-of-order execution and branch prediction, optimize your code very well even if your code is written quite inefficiently. So these are all very positive aspects of a CPU. Simple and complex instructions, easy to program, and can optimize your code well. But the problem with CPUs is you have a very limited degree of parallelism. Yes, you have a few cores. In each core, you may have a few pipelines. So you have some parallelization, plus you have other features at hand like SIMD. SIMD stands for single instruction, multiple data. So you have you can apply the same operation to multiple variables at the same time let's say one cycle, for example. So you can also get parallelization from here. But if you want to use SIMD, you also maybe have to write some more low-level code to take advantage of this. If you have a good compiler, and maybe the compiler can do this for you and also help you with pipelines and a few cores. But overall, there's a very limited degree of parallelism in CPUs. GPUs are pretty much the opposite. GPUs, they have a high degree of parallelism because in a modern GPU, you have hundreds or thousands of cores. So you can do extreme parallelism. But there are some challenges to this. It's relatively challenging to program code of that sort. You need to learn CUDA. You want to use NVIDIA hardware, or you have to learn some other environment and how to program for it. Then GPUs mainly execute relatively simple instructions like additions, multiplications, but not more advanced instructions. And GPUs are actually not that great in optimizing inefficient code. If you look at the number of transistors used in a modern CPU, you will actually see that probably around half of the transistors in a modern CPU are only used for things like branch prediction and out-of-order execution. Those are actually a big piece of modern CPUs. But in a GPU, typically you wouldn't see that kind of stuff, so they cannot optimize inefficient code at all, or they cannot do it very well. So it's even more important to write very good code for taking advantage of your GPU. So that's why I think that the statement that I heard here a few years ago, that CPUs have no future and the future only belongs to GPUs, it's probably not correct. When it comes to training neural networks, yes, probably GPUs are extremely helpful. But in general, CPUs are also extremely helpful because CPUs allow you to work on a large number of very different tasks, while GPUs don't really allow you to do that. If you look at some recent approaches, for example, from Apple with their M architecture, I think now M3, they're trying to blend these two approaches, CPUs and GPUs, into some kind of hybrid architecture, which tries to combine the pros of both architectures. However, if you want to write code for something like this, again, and you want to write your code efficiently, again, you need to learn the instruction set of the Apple CPU and how to write code efficiently for this. So this will not be done fully automatically for you. Maybe there is some help and some cross compilers, but probably if you want to take advantage of this, you still need to learn how to write code efficiently. Then you have all sorts of variations of GPUs, like, for example, a TPU. A TPU is a tensor processing unit. A tensor processing unit has the goal of processing tensors efficiently. So what's a tensor? A matrix is a matrix or a vector. They are tensors in 1 or 2 dimensions, and a tensor is, you can imagine, like a matrix, but in a higher number of dimensions, like, for example, a 3D matrix or something like this. These are kind of data structures you get to see when you write code for training neural networks or for making predictions in neural networks, especially maybe around convolutional neural networks. You would get to see such kind of data structures. Tensors and TPUs, tensor processing units, they were proposed to work with those kind of data structures efficiently. I think now we don't talk that much about TPUs in the last few years anymore, but rather if you look at GPU vendors like NVIDIA, like the V100, they advertise that they have tensor processing cores. So if you hear tensor, it's eventually just a higher order matrix. And those kind of cores, they're specifically made for processing such data efficiently. And when you write code in order to train a neural network, just make sure you do something we call vectorization, avoid loops as much as possible, use linear algebra operations instead whenever possible, like matrix multiplications, matrix additions. Don't try to build loops doing all of this for you, because something like this would be extremely difficult to parallelize if you use libraries for doing, say, additions, multiplications, and other operations for you, then that can be mapped more easily, for example, to a GPU environment like CUDA. So avoid loops as much as possible when writing such code. If you use Keras or TensorFlow, whatever, this is already a very high level of abstraction where this is taken care of you. But if you maybe need to build more customized code and you cannot use only these high-level features, try to use vectorization as much as possible and avoid loops as much as possible. And then eventually it will be far easier to parallelize your code by taking advantage of these cross-compilers in the libraries. There are other approaches to training neural networks efficiently. For example, there are FPGAs. An FPGA stands for a field programmable gate array. Field means customer. So an FPGA is a highly flexible piece of hardware. If you look at the opposite would be an ASIC. So I'm just writing this to the chat, ASIC, an application-specific integrated circuit. An ASIC would be a piece of hardware which is hardwired doing something you specifically wanted. If you want your piece of hardware to do something different, you need to rebuild it. You need to redesign it and rebuild it, which is slow and expensive. But the ASIC is extremely fast. An FPGA is a more flexible piece of hardware where you have flash cells in it, and eventually you want to combine these flash cells in a way so they represent the logic functions you want to implement. Can look something like this. You have your configurable logic blocks, which are eventually flash cells, and you need to combine these logic blocks in some way that they convert your inputs to the outputs you want. Now, I want to know from you, has any of you ever worked with FPGAs? Maybe thumbs up, thumbs down, if this is something you have come across already or not. So we got a thumbs up. Maybe you want to tell us, either you can turn on your mic or send us in a chat what you have used FPGAs for. I'm very curious to learn more about that. Please go ahead.
Oh, well, I'm an electrical engineer, so I used FPGAs in the past. Simply when I did not know what the actual digital circuit will be in the future. So it was simply more flexible to me. So it was a completely different field than it has nothing to do with data science or something.
Okay. Yeah, thank you. So you said it's highly flexible and you didn't really know.
I used VHDL, of course.
Okay, good. I'll say more about VHDL in a moment for the others. Thank you very much for your contribution. So we have this highly flexible architecture, and based on how we combine these flash cells, we can compute a different output based on the inputs. And how do we actually configure the flash cells so they represent the logic function we want? we don't really want to manually combine this. Rather, we want to use a more high-level language. And you mentioned VHDL. And VHDL is a hardware description language. Concretely, VHDL stands for Very High Speed Integrated Circuit Hardware Description Language, or in short, just VHDL. And it looks like a programming language, but it's very important. This is not a programming language, but it's a hardware description language. So you're describing the behavior of hardware with this language. It looks like a programming language, but what you're writing will not be a piece of software running on a CPU. Rather, you're describing the behavior of the hardware. So what the hardware is doing based on the inputs. And this logic that you're describing here can be mapped eventually into a layout for your FPGA. So based on which FPGA you're using concretely, you need to map this hardware description to a concrete routing of the FPGA. And it has the advantage that if it doesn't work exactly the way you want it, you can just change the hardware description and then map it again on the FPGA. So this is, I think, what you described. You didn't know exactly what the logic function you wanted to compute looked like. So yes, you can do this by trial and error. You don't need to build an ASIC, which then doesn't work, and you need to dump it. Rather, you're just changing the hardware description and you're mapping it again to the FPGA. And such FPGAs have also been used in recent years for training neural networks, which led to quite some speedups, which has lots of pros, also some cons. A pro can be you can configure the FPGA specifically for your training problem because you have a GPU. That's what we just saw. It's still a very generic piece of hardware, which could be used for training lots of different neural networks. And here with an FPGA, we could try to specifically route it so that it can train a neural network of our choice extremely rapidly. So this is a huge pro of such FPGA approaches. The cons are, again, you need to learn how to use hardware description languages. Maybe you can think about cross-compiling, that you have a high-level description, maybe in Python, and you want to map it to maybe a more specific VHDL code. You could be doing this. It's something that had a rise a few years ago, but I feel in the last few years, this has not become the dominant approach. GPUs are still more common, but I think there's a lot of potential around FPGAs and training neural networks that has not been fully exploited. One of the pities is, I think, in your AI program, the whole part of computer engineering is a little bit limited because you need more time to learn AI. When I studied computer science in my undergrad, there was actually a big focus on hardware and computer engineering. So I also learned VHDL. And I think one of the challenges, I think, for most universities is maybe to build the bridge between computer engineering and AI. And once we can enable more AI students to learn about hardware description and computer engineering in general, maybe we could also make this approach of training neural networks more popular. And I think there's a lot of potential because these FPGAs, they are powerful and you could customize them specifically to training a specific neural network. And you don't need to use such a highly generic GPU, which has, again, its pros and cons. But I think there's a lot of potential for you if you learn the foundations of FPGAs and VHDL. Probably there's a lot of opportunities for you to make money. So that one student who said he has a background in electrical engineering, take advantage of your electrical engineering skills and try to combine this with AI and maybe push such things like using FPGAs for training neural networks, because I guess many others are not able to do this or they don't have the skills to do this yet. So this could be your niche in the market. So we've discussed now FPGAs and hardware description. And I think there's a lot of potential for this, which we haven't fully used yet in the market. And that's your opportunity. Now, we've seen big data architectures, and in particular, MapReduce, and we have seen guarantees that NoSQL systems make, like Bayes, which is a contrast to ACID. In this chapter that we're doing now, it's called Big Data, Small Data, All Data. We will see some typical issues around data quality, especially biases in data. That's a topic that has got a lot of attention in the last few years. We will be investigating this. Then we will also look at small sample size problems. While they are small samples, they could still be huge samples, so it could still be some sort of big data problem. And when you have small samples, you run again into all sorts of issues when training your machine learning models, and we'll be discussing some of those challenges as well today. So where does the term big data actually come from? We have seen this when we introduced this course a few weeks ago, and we saw it came from some slide deck in the 90s. But the big data approach has become more popular in the last 20 years or so for various reasons. Around 20 years ago, there was a very famous paper that was called Scaling to Very Large Corpora for Natural Language Disambiguation. And that paper tried to distinguish natural language. And what they noticed in this paper was that the exact algorithm to do this was important, but what was also important was just to use ever larger data sets in order to learn this task well from very, very large corpora, what they called it in that time. And there's often some sort of approach or methodology derived from this paper in the community, which is something like, it's not who has the best algorithm that wins, it's who has the most data. These two sentences are not written like this in this paper. This is very important, but it's something that was sort of derived from that paper and the understanding of machine learning at that time. What do you think about this sentence? It's not who has the best algorithm that wins, it's who has the most data. Maybe send some comments in the chat or turn on your microphone if you agree with these two sentences, or if you disagree, if there's maybe partially truth to it, or if you partially disagree, whatever. I would be very happy to discuss this with you. And you also have a microphone. Maybe just turn it on and let us know what you think about this. Or if you're not brave enough, maybe send this in the chat if you think these two sentences make sense or they don't make sense. And I'll give you a moment and I'll see if any of you follows up, and then I'll be happy to discuss your views on that. So I didn't get anything in the chat yet, but maybe one of you, maybe the student from before who already talked to us about FPGAs, maybe you are brave enough to tell us a little bit what you think about these two sentences. It's not who has the best algorithm that wins, it's who has the most data. So no one is brave enough, so then I'll discuss it. Meanwhile, if you want to share anything in the chat, you're most welcome to do so. Well, I think there's some truth to that, because large data sets can be very helpful because they may come with a lot of variation for a problem, and like this, we could learn a better pattern. But definitely, the choice of algorithm is still important. because the statement is it's not who has the best algorithm that wins. I don't fully think so. So some algorithms are better than others for specific problems. But if we combine this with more variation in the data, that's also helpful. But maybe just having ever larger data is also not the right approach, because if we just add more and more data, maybe we also add a lot of wrong data and lots of biases. So maybe we need more representative data plus a good algorithm for that specific problem. And I think that what will help us to advance. So not just better algorithms and not just better or not just more data, probably more representative data with the right algorithm. That's what I personally, or this is how I would personally address these two sentences. So there's some truth to it, yet some challenges. And data quality is actually crucial. And just adding more data of low quality will not help us. And there are very common data quality issues that I want to discuss with you. For example, completeness. Oftentimes, if you have a very large tabular data set, maybe there are just some missing values or some not available value. That's a problem. Then we have consistency issues in real-world data sets. For example, we have contradictory values for the same entity. For example, sometimes dates are written like this, which is the year, the month, and the day. Then we see something like this, which we in Germany would often interpret as the day, the month, and the year. In the US, however, this is often interpreted in a wrong order, that this is the month, the day, and the year. So all of this is quite contradictory and ambiguous. And if you maybe crawl your data from many different sources, you would have these different formats. I personally prefer the first format much more because it's the year, the month, and the day. Because the second format for us in Central Europe, it would be the day, the month, and the year. But in the US, this would be often the month, the day, and the year. So this could lead to lots of issues. Then data may just not be valid. For example, negative age values. There was maybe some issue in the data processing, and then your data just doesn't make any sense anymore. Data may not be accurate anymore. It could be outdated, or it just doesn't make sense. For example, a customer who's born in 1800 something, probably that doesn't make much sense, and so forth. So these are common data quality issues. If you have more common data quality issues, feel free to share them with us. Either turn on your microphone or send them in the chat. And machine learning is eventually garbage in, garbage out. You put in the right data, you may learn a useful pattern. If you put in the wrong data or just biased data, incomplete, inaccurate data, you're just learning the wrong pattern. So it's garbage in, garbage out. And that's why you need to spend enough time in your machine learning projects early on data quality. Concretely, that's a phase we often call exploratory data analysis. Many of you who are taking my big data course this term, you're also taking the large AI group project this term in parallel. And there, one of your current tasks in the AI project is exploratory data analysis. It's a crucial step before training a model, because if you just train your model on garbage data, you're learning garbage. So you need to spend enough time on understanding your data, for example, by providing plots, by computing summary statistics, trying to find outliers in your data. And then you can try to correct for this or eliminate some of the inaccurate data, and then train your model on high quality data that is left. And like this, the quality of your model and its predictions will go up massively. Unfortunately, exploratory data analysis, I feel, is often not discussed very well in the machine learning literature, because a lot of typical machine learning books, they only discuss models and approaches, how to train these models, but they don't discuss much what you need to look into your data beforehand. So that's why we're also discussing it here in this big data course, that we have the foundations in exploratory data analysis, which you will also need in your AI group project, at least the ones of you who are doing this project with me this term. And I have one example here. What that data set is exactly doesn't matter. It comes from the bottling business, and it's about a PET bottle that was stretch blowed, and it's the thickness of the wall at a specific point in such a bottle and in a PET bottle. And from hundreds of examples of such bottles or instances, we can try to, and we want to learn something. The exact task we're trying to learn doesn't matter here. Rather, we have our examples of such bottles that were stretch blowed, and there's much more data, obviously, in the data set. And we just want to see, how does this data distribute? And in an exploratory data analysis, you would just generate a histogram of your data, and you would, for this data set, you would get something like this. And we see this is in millimeters. It starts at around 1.6 millimeters up to, I don't know, 4.8, 4.9 millimeters. And we see there is a peak around 2.7 or something like this, 2.8, where actually this seems to be the mode of the data, that just the relative majority of bottles have a wall thickness of something like this. And when you create such plots in your exploratory data analysis or other summary statistics, you as a data scientist, you don't necessarily know if this is right or if this is wrong. Why is there a peak here? And that's something you need to discuss with the domain experts, or for those who are doing the AI project, with your industry partner when you see such occurrences. Could be that this is simply, well, most bottles just look like this, and that makes sense. Could be. Why are there outliers? Why is there something like this? Was this an issue in the data processing? Was it just a very, very special project where very special bottles were blow molded? Are some really that thin or not? These are the kind of things you as a data scientist probably don't know. And that's why you need to talk to domain experts, which could be your customers, or if you're a data scientist in a company, you would talk to the domain experts. And there could be lots of other reasons why there's this peak around 2.7. Maybe it's correct, maybe not. You as a data scientist without the domain knowledge, you don't know. But you need to critically assess this, because this, if it makes sense, it's good, you can continue. But if it doesn't make sense, you need to wonder, what went wrong? Maybe something went wrong in the early data collection. Maybe something went wrong when you aggregated data sets, and so forth. Also, we have seen all these other common data quality issues like consistency, dates. That's something, especially if you work with dates, these kind of issues will probably appear all the time. You need to pay attention to that. And if you have a plot like this or some other summary statistic, maybe right, maybe it's wrong. And that's why I talk to the domain experts. And I have another extreme example, which was also from a stretch blow molding machine. And what we see, so I'll briefly explain probably what a stretch blow molding machine is in the bottling business. You all use PET bottles probably most of the week when you drink a Coke or a juice or something like this. And a PET bottle is created through a stretch blow molder, and a stretch blow molder uses a preform, which is a piece of plastic, and this one is heated up in an oven for a couple of seconds to maybe 100 degrees or something like this, and then it's stretch blow molded into a template and then cooled down, and then you have a PET bottle. And this is also from a data set about stretch flow models. And this was from one of my previous jobs, but I presented this kind of stuff at a conference. So that was public anyway, and we can put it here in this slide deck without any issues. You can also see where it comes from, where I worked before, but we talked about that kind of stuff at conferences. And what we see here is data of 540 stretch flow molding machines. And we try to predict something in the stretch flow or for the stretch flow molding machine. What exactly doesn't matter here, but there are all sorts of variables, and we have generated a scatter plot, or it's called a box plot. And yeah, sorry, it's a box plot. Yeah, and for this box plot, we had these 540 samples, and what we have in this variable is some kind of velocity of how quickly the bottle moves through this stretch flow molding machine. And we see that for these 540, the box plot doesn't actually show us too much, because a box plot should show us the mean or median, whatever, depending on the variation, and some variation in there, plus the outliers. But we see that here are the whiskers or whatever, and we have some extreme outlier out here. And from the rest of the data, we don't see much. And we see that from these 540 examples, we have a very strange distribution in there. The minimum is 0, so the minimum velocity is 0. The maximum velocity is 800 meters per second. But I don't think it's possible to move a bottle at 800 meters per second through a stretch flow molder. We would need a stretch flow molder that has a rocket propulsion. I don't think that's the case. And we see the mean is 1.79, and we have a standard deviation that is 34.4, which is huge. So we see something is probably wrong in that data set. And we wonder, where does it come from? When I worked with this data set, I then talked to the domain experts, and what they actually told us, so I wondered, where does 800 come from? And 800, it's precisely 800, by the way, was an error code. When they built these stretch flow molding machines, they tested them on site, and they measured how quickly the bottles move, plus obviously hundreds of other sensor values, and we tried to predict something, which doesn't matter for now. But we notice here that 800 meters per second must mean something, and I was told it's an error code. And an error code meant in that testing could not be measured. And 800 was an integer, however, it stayed in that data set and was not marked as an error. And if you just use this variable like this for predicting something, probably you will learn some pattern, but what you're learning will not make much sense eventually. So what you need is, you need to carefully examine your data set, and when these values don't make sense, talk to the domain experts. Fortunately, 800 was a value that large, so we could find it here in our exploratory data analysis, and we could filter out those examples. But imagine if the error code was 2, then maybe we would have not found it, because 2 would have been close to maybe the other values, and would have been very hard to filter this out. So very importantly, never mix up error codes and concrete measurements. Because if you mix up error codes as numeric values with numeric measurements, you will run into situations like this, and this will definitely ruin your data analysis or your machine learning model if you don't do a proper exploratory data analysis and you find these issues and you filter them out. Here we found it because the error code was 800, but if the error code was 1 or 2, it would have been very difficult to notice it. So pay attention to this kind of stuff. What we see here in the box plot is some other variable. Sometimes you may just have extreme outliers because we have the mean here, we have the whiskers, so we should have most of the data actually within here, but we have some outliers both to the bottom as well as to the top. And to the top, we actually have quite a few outliers. And now the question is, where do these outliers come from? So the maximum value is 143, the mean is 30, we have 605 examples. When it comes to these outliers, talk to the domain experts, the ones who have worked on this problem and measured the data. Maybe those just refer to very special machines, very special purpose machinery for very special customer requirements. If that's the case, maybe there's a reason why they look like this. Again, 143, maybe it's some error code or something went wrong when processing the data. What to do with the outliers also depends on your problem. You find a lot of advice in books or on the internet what to do with outliers. Some say filter out the outliers, just delete them. Probably it's not that easy in practice because outliers, there's a reason for them why they are there. Maybe it's just something in this variation of data that appears very rarely, but it may still appear. So if you filter out the outlier, maybe your model will not be prepared to handle these special cases in the future. So don't just delete outliers by default because they mean something. Maybe you want to build a special model for these outliers. Maybe you want to ignore the outliers in your default model. And if you're very extreme outliers, maybe you want to handle them in a different way. That could be a different approach, but don't just delete outliers as you sometimes read, because this will probably just lead to lots of problems once you put your model into production and let it work on real data. So those are a few words of mine on data quality. So don't underestimate the EDA, the exploratory data analysis, because it's certainly something you need to spend enough time on. Otherwise, it's just garbage in, garbage out. And doing an exploratory data analysis, there are lots of libraries already to generate summary statistics of your data or plots or plot outliers or correlation plots, whatever. So that depends largely on your concrete problem, but there's lots of libraries available that support you in doing this. And then what these outliers mean or what the plots mean, the interpretation is up to you, and you need to talk to the domain experts or your industrial partner, say in the AI project for those who are doing it this term. Don't underestimate this. Spend enough time on the exploratory data analysis. Now we will talk about another very common issue in machine learning: biases in data sets. When you train your machine learning model, obviously your training set is different to your test or production set. The two sets are typically different, and there's a good reason for that, because you want to generalize from the training set and then make your model work on a test or production set. And that's extremely common, but something, and you all know about this, but something that probably you know less about is what happens if these two distributions are different. Meaning your training set is from a certain distribution and your test set is from a different distribution. And if these two distributions are different, then you run into various problems. And in practice, this appears, and that's what we call a bias. So a bias means that the distributions of your training and test set are different. Some of you, at least I see some of the names of you here in the participants section. I think some of you have attended the CERN Spring Campus a few weeks ago. If you have, maybe just send me a green sticker or just see who of you actually attended the CERN Spring Campus. Already got a reaction. And so for those who have attended a CERN Spring campus and attended my lecture there, that's exactly one of the sections I talked about in my lecture there. So that's a little bit of a revision for those who have taken the CERN Spring campus, but those who did not attend the CERN Spring campus, it's totally fine, because my lecture was just one of many lectures in there. And we're anyway starting with the issue of biases in here from scratch. So what does that term bias actually mean in machine learning? In recent years, I feel this term bias has been used from a highly, say, political perspective, claiming that machine learning models discriminated against something of a certain race or gender. And I feel that term bias is just highly politically used now, but the term bias actually has scientific meanings in machine learning. And when we talk about bias, I actually noticed that the term bias may mean many, many different things in machine learning. Bias would mean that the distributions of our training and test or production sets are different, but there are totally other occurrences of the term bias. For example, every machine learning model makes an inductive bias. An inductive bias means your model makes some assumption when it learns. For example, logistic regression assumes that the training data is linearly separable. Linear regression makes other assumptions. When you have a support vector machine, the support vector machine makes certain assumptions. A decision tree makes certain assumptions. And these assumptions about your data is something we call the inductive bias, because every model is a simplification of reality. And that simplification is the inductive bias our model makes. And we always have some inductive bias. Sometimes in the literature, the term bias is used as a synonym for underfitting, whereas overfitting is sometimes called variance in the literature. Bias sometimes means underfitting. Then I found another occurrence of the term bias. If you have an hypothesis, something like this, say as a hypothesis in linear regression, for example, as well as other models, you have your vector x and you want to predict something for it with your hypothesis. We say, well, weight 1 times x1 plus weight 2 times x2 plus weight n times xn, plus we need our shift or y-intercept, which we call W0. And this parameter W0, which is the shift or y-intercept, is sometimes also called bias in the literature. So we see that term bias in machine learning may mean many different things: inductive bias, underfitting, this y-intercept, and so forth. In this lecture, however, the term bias will mean something different. It will mean that the distributions of our training set and test set are different. So that's what we are now referring to when we talk about biases. Biases are actually a major issue in machine learning. And if we have biases in our training set, meaning our training set is not representative for the test or production data, then we are making some assumptions and our predictions could lead to lots of problems. There could be a lack of reproducibility. There could be a lack of generalizability. Our models may discriminate against something of a certain race or gender or whatever, because maybe those people are not represented very well in our training data. Those issues are not just in machine learning. It's been argued actually in a paper some years ago that most quantitative research published is actually wrong because the data set used was maybe not representative or biased to some extent. So that could be the case. I'm not making the claim that most research published may actually be wrong, but if your data set is biased, you're obviously making some biased conclusions from the data. So in machine learning, as I said, this may mean that machine learning models may just discriminate against someone, or someone may not be getting what he or she could be entitled to, especially underrepresented categories. Now, the issue of bias is nothing new in machine learning. It's actually an issue in statistics ever since. And before we look at biases in machine learning, I want to discuss some biases in statistics with you. If you look at elections, not just in the US, but also in Germany, you have all these forecastings or predictions of what an election, of what the outcome of an election could be. This is nothing new in the early day in our world nowadays. Such predictions have been done for about 100 years or even longer, especially in the US. In 1936, there was a presidential election in the US, and Roosevelt was running for re-election. He was elected in 32 and then was running for his second term in 36. And he was from the Democratic Party, and his challenger was from the Republican Party, and his challenger was called Alfred Landon. He was the governor of Kansas at that time. And there was a famous magazine, the Literature Digest, and that magazine had correctly predicted the outcomes of the elections in 1916, 20, 24, 28, and 32 based on polls. So in 36, they wanted to predict the election again, and they sent out 10 million questionnaires in order to predict the outcome of that election. And they received 2.3 million returns, and they predicted that Landon would win. Now, most of you, or probably none of you, have ever heard about Alfred Landon before. You only heard about Roosevelt. So probably it didn't work out very well for Landon in that time. And in fact, he actually lost the election. This is what the result looked like. So Landon only actually won 2 states, and Roosevelt won the other states. So major win for Roosevelt, major loss for Landon. So now we have a couple of questions. This magazine, the Literature Digest, they correctly predicted the elections of 1916, 20, 24, 28, 32. So people had a lot of confidence in this prediction from 36. So there are a couple of questions that may arise. How could this go wrong despite 2.3 million participants? And how could the Literature Digest actually collect 10 million addresses in that time? So this was really a big data analysis for that time. 10 million addresses, they needed to get them from somewhere. And 2.3 million people responded. And that data had to be processed. The Literature Digest actually made sure that they counted correctly and that they processed the data correctly. So that was not the issue. But let's start with the question, where did they get that data from? They went through car registrations and phone directories to get addresses of potential voters. Now, in 1936, those were disproportionately wealthy people because most people in that time did not have a phone and did not have a car. So the ones that had a phone or a car, they were disproportionately rich and extremely favoring the Republican candidate, Landon. That was a major bias, the way they collected these 10 million addresses. But what they also noticed later on was that those who favored Landon among those 10 million recipients in particularly wanted to respond. So the ones that favored Roosevelt rather did not respond. It was only understood in the 1970s, so like 35 years later or 40 years later, what exactly went wrong in 1936 with these polls. So in that time, it was noticed that something went wrong in 36, and people lost confidence in this magazine, the Literary Digest, and it actually disappeared very quickly then because people lost confidence in it. But a statistical analysis of what went wrong and a full understanding of how this poll went wrong was only understood in the 70s. So it took quite a while, the statistics community, to catch up. Now, we saw this big data analysis did actually not succeed. And in 1936, there was a second person trying to predict the election, a man called George Gallup. And he, Gallup, only picked 3,000 potential voters. And he tried to pick those 3,000 people as unbiased as possible. So he tried to make sure that poor, rich people and people from throughout the whole country with all sorts of different backgrounds tried to or were in the sample. And he handpicked them and interviewed them. And he could actually extremely well predict the outcome of that election, just with a sample of 3,000 voters rather than a sample of 10 million people. So we see that just having ever larger data sets is not the solution to all of this. Maybe just having a smaller and more representative data set could lead to a better result. That's why spend enough time on your exploratory data analysis, because we see this is an issue that has always been in statistics, and now it's also relevant to machine learning, because we collect ever larger data sets, but maybe they're not representative. So rather pick a smaller data set that is more representative and check your exploratory data analysis and see if there are any anomalies in the data, and always ask yourself the question, where did this data come from? This kind of wrong prediction happened more often. For example, in 1948, Truman ran for re-election, and his in a newspaper here, the Chicago Daily Tribune, predicted that Truman would be defeated, and they already printed the magazine in the night because they were so sure that Truman would be defeated, but they also did the polling wrong and their prediction was wrong. And here you can see Truman, who's extremely happy that he actually won and that the newspaper that appeared the next morning was wrong. The same thing, that polling was done from a heavily biased sample, was in 2016, where one newspaper here already printed, "Good morning, Mrs. President," because they predicted, as many others predicted, that Clinton won, and in fact, Trump actually won. So you saw this happened in 2016 again. Had also to do with heavily biased data or heavily biased set of voters that were picked in order to predict something that maybe the media also wanted to see happening. I don't know, but certainly they picked a heavily biased sample, and they printed the magazine or the newspaper in the night already. And in fact, Trump was elected and not Clinton. Now, the issue of bias can also be described in machine learning. And we will now look at biases in the context of supervised learning. As you know, in supervised learning, we have our input data X and our label Y, and we have a pair of this. So I put the index here that I have an X and a Y that belong together. And X is in bold because it's a vector, because it could be more than just one entry. It could be multiple entries in that sample. And we have a corresponding label Y. And we are drawing this data from a training distribution, P-train, and where capital X denotes the data and Y the label. Now we have our training data, which is obviously different to our test data, but we care now about the distributions. And if our training data comes from a distribution that is different to the test data's distribution, then we have a bias. So it's not about that the two sets are different, because yes, for sure they are different. But what we care about now is if the distributions of the training and test sets are different. And if they are different, then we have actually a bias. Now we want to correct for this bias. So we have a training set and we know its distribution, or we try to estimate its distribution. So you can also estimate densities, for example. That's something you can find in various machine learning libraries. You have a data set and you want to infer the distribution where it comes from. If you can estimate your training distribution and also your test distributions, or where your test data comes from, or your production data, you can try to calculate a weight for each of your examples in order to determine how important a training example is or how unimportant it is. And if you can do this, you can calculate what's the probability of my training example appearing in the test set or in this test distribution, and what's the probability of my training example appearing in this training distribution. If you can calculate these probabilities, you can actually divide the test one by the training one, and then you have a weight. And this weight is an importance measure of how important your training example will be. Now you're wondering, how can you actually use such a weight? If you take a look into, for example, scikit-learn, you can look at various classifiers and you can see how to add a weight. For example, if you go to scikit-learn and you go to the documentation of logistic regression, you see all these parameters you can pass to when you initialize the model, but you also have three parameters for fit. All of you have used X and Y, your input data and the label vector, but you also have another parameter which is called sample weight. It's not offered by all models, but by some. And I don't know if you have ever seen this parameter sample weight in some of the models. If you have, maybe send me a thumbs up or thumbs down if you have not come across this before. And what you can pass here is another vector, and it's the weight of each example. So you can say how important the example is when doing the training. You don't need to pass it, it's optional. And if you don't pass it, each example will just have the same weight. But in this model, you can do it. And what you would pass here is exactly this weight that I have shown you how to calculate, where you would say how important an example is. Here, this would be to address the bias. You could maybe use it for some other applications as well. Maybe just say some examples are more important than others, but probably this would, again, address some bias. And just for correcting for this bias, you can calculate these weights and you can pass them. So feel free to try this out and see how this sample weight parameter in scikit-learn works. Now, it looks easy. We just infer these distributions and we try to calculate these probabilities and then the weights. However, it turns out it's not that easy in practice, because calculating these probabilities reliably means you need to reliably estimate the distributions where they come from. And that's not that easy, in fact, because these distributions may be high dimensional. because X is a vector. It's not just a single entry, but can be many, many entries. And then you're dealing with the curse of dimensionality, something you come across quite often in the field of machine learning. And here you would come across the curse of dimensionality again, because estimating from a limited number of samples, these high dimensional distributions can be very tricky. So we need to make some discretion, some assumptions about the bias. And if we make that, then it actually becomes easier to solve the bias. One concrete bias that many of you have come across is called class imbalance. And class imbalance means you have in a classification problem a different number of examples per class. And we will now describe this in terms of our highly generic framework that we have just built, this one here. So an example of class imbalance could be we have a two-dimensional data set, and we have one class and the other class. So this is plotted here. And we actually have much more examples of one class than the other. And if that's the case, and you train your machine learning model directly on such a set, you will also make heavily biased predictions. Maybe sometimes that's something you want to do based on your use case, but in other use cases, this may just lead to lots of unexpected behavior. So depending on your use case and your goal, you may have to debias this data set. And we can just use our weighting approach from before. And what we need to do is, because I said that we have these very complex joint probability distributions, especially where X may be multiple dimensions, we can make some discretion. And we can say, rather than calculating this weight like this, we will calculate it in a slightly different way. And we could say, well, actually, what we care about is that the distributions of labels is only different. So the distributions of labels among the training or the training distribution of labels and the test distribution of labels is different. But we will also say that we have now conditional probability distributions. Concretely, the probability distribution for the data given the label is the same for training and test. Because we're now trying to break up this joint probability distribution. And we're saying, well, these conditional probability distributions are the same, but the label distributions are different. And if we do that, we can severely simplify the calculation of our weights. Because as you remember, if I have a joint probability, I can break up a joint probability into a prior and a conditional probability. So the probability of X and Y can be broken up as the prior of Y times the conditional probability of X given Y. And if I do this, so I break up the disjoint probabilities distributions for testing and training into the data given the label times the prior of the label, then I can simplify it, because what we just said in the previous slide is that these conditional distributions of the data given the label, they are the same. The same for testing and training. So I can just eliminate them because I have the same in the numerator and the denominator. And what I have left are just these prior probabilities. And I can just calculate that, and what I get is a weight. And calculating this weight is now very simple, because all I need to do is I count the labels per class. And if I have done this, I have my weight. I can plug in the weight for training. I could do also other things with the weight. I could use the weight, for example, for undersampling or oversampling in my training set. So undersampling would mean I remove the examples of which I have too many of the one set. Oversampling would be, I would just be, in the simplest case, just be copying examples of the underrepresented class. I can also combine undersampling and oversampling, for example, with an algorithm called SMUTE. It's the synthetic minority oversampling technique. It's a combination of under and oversampling, and I try to create synthetic examples of the underrepresented class. This is an algorithm that, say, gets mixed reviews in the community. Some people like it, others, they don't like it too much. It's just one of many opportunities you could be using. You can also just use this weighting approach when training the model. So there are lots of different methods at hand for correcting for your class imbalance. Then there are much more kinds of biases. So there's not just our class imbalance. There are other biases. For example, covariate shift. Covariate shift refers to a totally different kind of bias. And I want to start with this plot here. What I have in this plot is, again, a two-dimensional data set. It's an x1 and an x2 axis. And I have my training examples and I have my test examples. So this time it's not about a label, it's just about how the training data is distributed in that space and how the test data is distributed in that space. And if I look at that, I see that training data is distributed quite differently to the test data. And this kind of bias is something we call a covariate shift. And we can also describe the covariate shift in terms of our framework. We can say the distribution of the training and test data, so just the input data, X, is different. But we assume that the conditional probability distributions for the label given the data, so Y given X, is the same for training and test. And what I can do here again is I break up this joint conditional probability distribution, which is X and Y, and this time I break it up into a prior X times a conditional probability distribution of the label given the data X. And we just assumed in the previous slide, again, that the label given the data is the same for test and training. So again, I can just cross them out. And what I have left are these prior probability distributions for testing and training, just for the data X, and it has nothing to do with the labels anymore. So I can calculate these weights more easily. It's easier than before. However, it's still tough because what I have eliminated from this problem is the label, because the covariate shift has nothing to do with the label, but only with the distribution of the input data X. If X is just a single dimension, you can probably calculate this quite easy for most real-world problems. But X could be a high-dimensional vector. And if that's the case, calculating this can still be extremely tricky. And in my PhD thesis, like 6 years ago or something like that, I proposed an algorithm that could estimate this one more reliably and more efficiently. It's just a detail. It doesn't matter for this course in big data. But what you should be aware about, if we calculate the covariate shift, or if we assume the covariate shift, calculating this is easier, yet it's still probably trickier than for the class imbalance, because X could be a vector. If you are interested in the issue of biases in big data, I published a paper, a survey paper 6 years ago. You find it on the internet, and I think I also uploaded it into the Nextcloud folder of this course. And in my survey paper, I'm reviewing the issue of biases in big data. And I've checked, it's not in the Nextcloud directory, but I will upload it later, or you just find it online. So if you just search the paper, Impact of Biases in Big Data, It's open access, so it's not behind a paywall. You can find it, and you get a good review in about 10 pages of what's the issue of biases in big data. I discuss covariate shift, I discuss class imbalance, plus many other kinds of biases, because they're not just these two kind of biases. How to detect the kind of bias, like do you have class imbalance, do you have covariate shift? That's something you would be, again, finding in a exploratory data analysis. For class imbalance, you could just count the number of examples per class, and then you could see how to address it. For covariate shift, this is something that can be measured. There's some ways to measure it, but you could also just plot your data set. If your data is more than 2 dimensions, if it's a high dimensional data set, you could map it to a 2D representation and then visualize it to get maybe a glimpse if there is a covariate shift in it or not. Mapping a high dimensional data set to a lower dimensional data set, you could use PCA, the principal component analysis, or you could use t-SNE. I'm just writing these into the chat. t-SNE is one approach to plotting high dimensional data sets in 2D or 3D, plus there are many other algorithms for doing so. And these are all the kind of things you should be doing in an exploratory data analysis in order to get a better understanding of your data set. I also want to share with you where I came across the issue of biases. So I did a whole master's in machine learning, and in this master's, class imbalance was briefly discussed, but not the issue of biases as a whole. And when I did my PhD, I started to notice the issue of biases in data set at a much bigger scale. In my PhD thesis, I worked on the detection of electricity theft. And we talked about this already in the introduction of this course a few weeks ago. So what happens is people manipulate power infrastructure, say their meter or a transformer outside, with the goal of getting electricity for free. And this was my PhD thesis. The work was on building a machine learning model that could detect electricity theft better than those previous expert systems that the industrial partner used. And I started to come across the issue of biases. I'll describe this now with a simplified example. Imagine this is some state in Brazil, for example. That's where the data came from that I worked on. And imagine we have a big city. So for now, it's simplified. We just have 2 cities. We have a big city, which is here along the coast. So big city is this big black circle. And we have a smaller city more inside the country. And now I can carry out a certain number of inspections per year, say 1,000 inspections. And maybe I have most of my technicians in the smaller city and I'm carrying out most of the inspections there. That's why I have the large magnifying glass in the big city, in the small city. And in the big city, I just have a small magnifying glass. That means just a small number of the inspections are carried out in the big city, while most are carried out in a smaller city. So this is how you should understand this figure. Now, the consumption behavior of the customers in the big and small city could be different, because maybe I need a lot of air conditioning all year long in the big city because it's just too hot both in summer and winter there, because this is somewhere in Brazil. There's a lot of humidity maybe there, both in summer and winter at the coast. But inside the country, it's maybe not that hot in the winter. So maybe I don't need air conditioning in the winter, maybe only during the summer. So the electricity consumption of the customers is quite different. But I carry out most inspections in actually the underrepresented city. And like this, I'm already collecting a bias. Now, the bias is much more complex because I not just have 2 cities, I have a lot of cities. but the bias can address more issues. For example, some meters or some types of meters are easier to inspect than others. So, or some kind of meters are easier to manipulate than others. And when I maybe inspect the meters that are more easy to check than others that are more difficult to inspect, I'm again creating a bias. Maybe I'm carrying out most of the inspections in winter, not in summer. Again, I'm creating a bias. So like this, I'm easily creating a high-dimensional bias when collecting all of this data. And then if I just train the model on the data, I will create a massive bias, and I will make massively biased predictions that will cause all sorts of problems. It will lead here to maybe unnecessary inspections, which will lead to a loss of revenue, unnecessary costs. If you have this with, say, personal data, maybe I'm discriminating against a certain segment of our population, or it could be perceived discrimination, whatever, depending on the use case. So make sure when you collect your data, try to collect it in an unbiased way, or as little biased as possible. There will always be some bias probably in your data, but try to reduce that and pay attention to collecting your data, and keep the bias low. If you have a bias in, try to filter it out when you train the model. Try to address this in your exploratory data analysis, and have a look at my survey paper, which discussed all of that in that time. The paper was from 6 years ago, but the issue of bias, I think, is even getting bigger, because more and more people are now doing machine learning than 6 years ago, but most of them are not aware of it. I think it's something that is not discussed a lot in a lot of machine learning courses, or it's not discussed a lot in whole AI programs. That's why I'm discussing it here in the big data course. The theory has not really changed in those 6 years. The theory has actually been there for a long time. What has changed compared to 6 years ago is that there are more and more libraries assisting you with detecting and reducing biases in your data set. So there has been some progress with regards to this, but keep a look at it, and hope it will help you to become more successful when doing data science in the real world, and build better models that have a better predictive power and are less creating maybe less discrimination. So take a look at that. It will certainly be helpful for your career. The field of big data has received lots of praise, but also lots of criticism. There's a very critical view from Michael Jordan, one of the machine learning pioneers or AI pioneers. He was interviewed by IEEE Spectrum about what he thinks about big data, and some years ago, and he wasn't too positive. Something I notice around the big data world is we see a lot of people who a few years ago claimed that all the problems we have in our world could be solved just through big data experiments. We collect ever bigger data, and we could just learn everything from these data sets. I was always very skeptical of this, because I said just having larger data sets will not help us anything. We would rather need more representative data, even if that data set is smaller than. However, there were people in the Silicon Valley, they got a lot of funding for all these big data startups, and most of them didn't work out eventually, because just collecting ever larger data sets doesn't solve a lot of problems. Rather, it creates a lot of new problems. And now the same people who had collected all that funding, they keep saying now, we need smaller data sets, and that would be the solution, and more representative data sets. So it's somewhat just a bit, I don't know, confusing that these people now just want exactly the opposite of what they wanted 10 years ago. And what I noticed, like maybe 5 or 6 years ago, and it's still true today, that even a lot of AI professors, they are not really aware of the issue of biases in big data. And that's why it's something I'm trying to discuss here in this course. So pay attention to this and make sure you build more representative models, even if it's a smaller data set that you are collecting or retaining. Probably it will lead to better results than just collecting ever larger data sets. If you can collect a large data set that is representative, that would obviously be cool, because then you may have a little bit more variation in your data. But first of all, make sure you have a representative data set and not just an ever larger data set with more and more biases in it. Now we will come to another subchapter in here, which I call small sample size problems. What we have seen in this course is, so far, we have plenty of data for training models, and we train these models on large data sets. Maybe we remove the biases, we use GPUs, and then we train a huge neural network, for example. However, it turns out that it's not always that easy, because for some problems, we may just have very, very small amounts of data available, or say very small amounts of samples. Maybe these samples are still huge, and then it could still be a big data problem. But even if these samples are small and we just have a few of them, we could run into lots of problems. So if we have a small data set with just a few samples, it's maybe not a big data problem, but I still wanted to put this in this course as a contrast to other big data problems, because I just didn't see where else I should put it. And we're now talking about so-called small sample size problems. And small sample could mean that the samples are still huge or not, but we just have a few samples. And in fact, we're coming across such small sample size problems, for example, in biometric identification, where we just have a few samples per person. Or we have CT scans. CT scans are expensive and difficult to collect, so maybe just have a few CT scans, but we still want to learn something reasonable. And what are consequences of such small sample size problems? When we try to learn from them, this could lead to poor results. We just don't generalize well. Maybe overfitting could be the cause of this, because we have much more parameters in the model than we actually have examples. So this could lead to overfitting and poor results. If you look into neural networks, you know how to address them, for example, by using regularization techniques, by using dropout, or all sorts of other things. You could, for example, do data set augmentation, meaning you take your data set and you add some variation to it. So you copy examples and you add variation, and then you artificially create more data, more samples. All of this could be done in order to address the overfitting or the poor results. But it could even happen that for some models, you're not able to train them at all if you don't have enough data. So you're not just getting bad results, but you're not able at all to train your model. And this can happen for a certain class of machine learning models. And I want to discuss this with you in the context of linear regression, which you're all familiar with. And we will see now today 2 ways of how you can train a linear regression model. And just as a quick revision, because we always have some students in here who are not from the AI bachelor's program, in linear regression, we want to compute a linear regression function. In my definition, I say we have m many training examples and we have n many features. And this could look something like this, for example, from housing price estimation. Here we have maybe, I don't know, like 30 or 40 examples. So m is around 40, and we have one feature in here, which is the house size in square feet. And we have a corresponding label, which is the house price in thousands of dollars. And we see that there is some linear correlation between the house size and the house price. If the house size goes up, the trend is that the price goes up too, but obviously this is not a perfect correlation because sometimes we see the size goes up and the price goes down because there are obviously much more factors contributing to the housing price. The input is a vector here in this example here, or the inputs are vectors. Here in this example, it's just a single variable, but we could add much more variables, maybe not just the house size, maybe if the house is in a good shape or a bad shape, maybe the number of rooms, some area about the neighborhood, and so forth. So, and with linear regression, we have labels that are continuous, and we want to learn to predict that label. And once we have trained our model, we can do a prediction. And our hypothesis is H, and we pass again our vector for which we want to predict. And it's pretty much what we have seen before when we looked at biases. Here it's just slightly more generic because we say we have our weight 0, and this is again our y-intercept, our shift. So we could just leave W0 here alone, or we just multiply it with x0, and x0 is by convenience just 1. And we can say then there's a next weight times x1 and so forth up to weight n times xn. And we could just describe this as the product of the weight vector and the input vector x, and that we can simply write this as a product of the two vectors. By definition, or for convenience, we say x0 is 1. So we can describe all of this just as a product of these two vectors. And we can have an example here. We could, for our data set from before, we could say that this y-intercept is 246. Then we have our weight 1, which is 0.2, and we have a house that has 1,500 square feet. That's its size. And in order to predict its price, we just multiply this. We have our input vector x, and we predict it, or we predict the label, which is 594. And somewhere we need to get these weights from, and we get these weights from training our model. And I will, I think, write this out on the iPad now. So we develop it step by step. The first part is a revision of linear regression for you, and the second part will be the new part then. So we will have our linear regression. And we have an error function or cost function, whatever we call it. So we have our error function, we have these weights, and we then go through all these examples. And the error function is meant to determine how good or how bad our model is right now. So we have our hypothesis for these weight vectors, and the hypothesis we put in our example xi. We go through all these examples, we predict a label for that example, and we have a difference to the correct label from the training set. We have the difference of these two, and the difference could be 0, it could be positive or negative. And that's why what we often do is we just square this error, and by squaring the error, we make sure that the difference is 0 or greater than 0, and small errors contribute little, and big errors contribute even more. And what we sometimes then do is, because this error term or this error value may just get extremely large, sometimes we just divide it, for example, by m, because we have m many training examples, or sometimes just for convenience later when taking the partial derivatives, we say we divide by 2m. And now I want to know from you, maybe without looking at the slides, how can I find a good weight vector W? So this is a vector. You also see this in the slides. It's in bold because I need multiple parameters. Which method would you typically use to find the weight vector so that our model fits the training data well? If you have any suggestions, which approach you would use, please send it to the chat or turn on your microphone. We got a suggestion here, backpropagation. Well, backpropagations is for neural networks. This is a linear regression. Well, linear regression is maybe a special case of a neural network, but yet let's simplify this a little bit. One approach is we take the derivative of the error term by weight, and we try to calculate the minimum. Yes. Does that approach, so the second approach has a name? So which approach, how would you call this approach in one word? It's certainly something you have seen before. If you, I don't know, have taken my computer vision course, there we discuss this algorithm in a little bit of a greater detail. It's I'll wait if anyone else has a suggestion what we want to do or how to call this. This approach that was described by the second student is gradient descent. So who of you feels familiar with gradient descent? Maybe thumbs up, thumbs down, but it's certainly something we have discussed in my computer vision course, and you have taken a machine learning course so far, so you should all have seen this. And gradient descent is a numerical optimization technique, and we briefly look at it just as a revision, because then we get actually to the small sample size problem. So we are doing a loop until convergence. And what we are doing is we have our parameters in the model. We go through each of them. It's the weight J, and we take the weight J and we subtract the partial derivative of the error function. So this is a partial derivative of the error function along the weight J. And I subtract that. Typically, I multiply this with alpha, the learning rate, and I'm doing all of this simultaneously for all J. So I'm doing this for all the weights, and I stop this loop when I'm converged, meaning that none of these weights changes much anymore, or only within a certain threshold and within a certain epsilon, and then I'm done. For my gradient descent, I need something more concrete now, because for gradient descent, I have this error function here. I'm just highlighting this again, this error function, and what I need is a partial derivative of that error function along my weight. Concretely, I will not derive this now, because how to derive this is something you would learn in a machine learning course, but I'll just write it out. So for my linear regression, this would be minus alpha, and then this term here will become more concrete. Concretely, I will do 1 divided by m times the sum of I from 1 to m. I have my hypothesis for the example xi. I have the label, and I multiply this with xj of I. This is something you can simply derive on your own if you take the partial derivatives of this term here. This xi back here, it will come from when you look into the hypothesis, which is here, and take the partial derivative of that part, and this will fall off. We have this 2 up here, and we have this 2 down here. When you take the derivative, that 2 will go, it's 2 times the sum, but because we had conveniently put 1 divided by 2m, these 2's will just cancel out, and that's why there's no 2 down here anymore. And this is our gradient descent for linear regression. And this one works okay for a small sample size problem. It will still overfit if you have a lot of parameters and you just don't have enough representative examples. This model will still severely overfit, but it's certainly trainable. Not sure if the result is actually quite good, but that's a different topic. You can add a regularization term, for example, to the cost function. So you would add something here plus regularization. That's also something you see in a machine learning course. What often would be done is, for example, adding a sum of all these parameters. For example, it could be something like this. I go through from I, well, maybe not I, let's call this J up here, from 1 to n. So I go through all these parameters and I take the weight J. Sometimes I square them, or I take the absolute value, depending on if you do L2 or L1 regularization. And you would often have such regularization factor like a lambda. I guess all of you have seen this regularization. Maybe thumbs up if you remember such a regularization or not. Or thumbs down if you don't remember regularization, but this is something quite common you would see in an introduction to machine learning. And if you do such a regularization here, this would allow you to maybe address overfitting to some extent. Maybe again, give me a thumbs up or thumbs down if you remember such a regularization. Also, if you don't, because I didn't get any positive responses so far. But should have definitely been addressed in your introduction to machine learning. If you don't remember it, well, that seems like it wasn't covered in your machine learning course. Good, then I'll say a few words because I don't teach the machine learning course, but you've all had that course. So what I've added here is a regularization term. And the idea of regularization is something like this. I'm summing all the weights together on top of the first part of the error function. So I add this to the error, and that means if I add very large parameter values, then the error goes up quite a lot. And a larger error is something I want to reduce. And an understanding in statistics is, or in machine learning, the model is more likely to overfit if I have very large parameter values. And that's why I sum the parameter values on top. One approach is that I take the value squared, which is an L2, L2 regularization. So I'm just writing this here. I'm taking the weight squared. I can also take the absolute value. This is then an L1 regularization. And what's the difference? With an L1 regularization, I tend to learn a sparse model. So a sparse model would be a model in which most parameters are 0, and just some of the parameters would have a value greater than 0, while the L2 tries to use all the parameters in the model. There are much more regularizations possible. And just one more thing is this lambda. It's the regularization constant. It's a constant in a model like you have your learning rate alpha. And your learning rate alpha is something how much you take the gradient into account, or this partial derivative into account. And here we would say how much we take this regularization part into account. Typically, lambda is also a small value, like 0.1, 0.03, and you would experimentally find it. And if you have large parameter values, this regularization part would get very large, and then you have a high error and you want to reduce it. And if you add it like this, typically the linear or the gradient descent will also reduce your weight values, and the model will be less likely to overfit. So this is how we could address overfitting in a small sample size problem. Meanwhile, I got a comment from a student here in the chat that they had seen the sum of absolute values. So that's what was discussed in your machine learning course. That's the L1 regularization. And there's also the L2 regularization plus many more. So this is how we can address small sample size problems when we use gradient descent. And there is one completely different approach to training gradient descent. So one is gradient descent, and the other one is an approach we call the normal equation. And using the normal equation approach, we can also find the weight vector. And what we are doing is something like, I'll show you this. I have my weight vector, and I can find it through this gradient descent approach, which is a numerical method. But the normal equation is a closed form solution, and I'll write it out, and then I'll show you what it does. So I have X, which is my input matrix. So it's rows, and each row is an example, and these columns are the features in an example. And I multiply X transpose by X. I invert this, and I multiply it again with X transpose times Y. If you check this in the slides, there it's formatted nicer because all of these elements are vectors or matrices, so they are bold. In bold, something for me is a little bit more difficult to write here on the whiteboard. But W is the weight vector, X is a matrix, which is the input, and Y is the label vector. Has any one of you ever seen such a normal equation? Maybe thumbs up, thumbs down if you have ever seen this in a paper or book. So one or two have seen it. And this is a closed form solution of linear regression. It has various pros and cons. First of all, it requires no loop. So it's something more definite maybe than a loop, which I don't know how long it takes until conversion. I don't need a learning rate because in my gradient descent, I need this learning rate, which I need to find experimentally. In order for gradient descent to work efficiently, I also often need some feature normalization or feature scaling. That's something I don't need here either for my normal equation. But the normal equation may be slow when these matrices get very large, because matrix inversion is O of n to the third, at least the naive one. If you use the Strassen algorithm, you can do it a little bit faster, but matrix inversion is slow. That's at least the essence of this. And you're wondering, where does this normal equation come from? Why does it look like this? And what I want to show you is just an intuition. Very important. What I'm doing now is not a derivation, because if you derive the normal equation, you need to do quite more. You need to do derivatives on these vectors and matrices. So you need this matrix cookbook, if you know it, to look into it. But I'm just showing you really a intuition. What I want to do is I have my matrix X, which are rows of examples, and I multiply this with a vector W, and these are my labels. That's what this is just simple predicting in my model, because X, we can write down X, I have M many rows and N many columns. So the examples are rows in here, and W is my weight vector, and I'm multiplying these two, and eventually when I'm multiplying the first row with this vector, I get one scalar value, which is one label. And if I'm multiplying the matrix row by row with the vector, then I'm getting a label vector. So this is exactly the predicting I'm doing in such linear models. And the intuition can be now, so I'm writing this again, and I'm multiplying something from the left on both sides, so X transpose, and I'm again multiplying something from the left. So I'm just moving all of this a little bit, and we're developing it step by step. And now I'm multiplying from the left an X transpose X and invert it. And I'm also multiplying this from the left. And what I'm seeing then is I have X transpose X inverted, and I multiply from the right X transpose X. So these two parts just cancel out. And then I have my weight vector, which is X transpose X inverted times X transpose Y. Very important. This is not a derivation. It's just sort of an intuition where the normal equation comes from. If you want to derive the normal equation, you need to do something far more complex, which is beyond the scope of this course. And now we will discuss a little bit, and for this I'll switch back to the slides, what the issue of the normal equation is for a small sample size problem. All I had shown you on my iPad is already well formatted here in the slides. This was the cost function or error function on the iPad. I called it E, but you can also just call it J, whatever. And we have seen there are two ways how to optimize the weight vector, gradient descent, and the normal equation. This was our gradient descent that we had written down. And this is the intuition of the normal equation. And the normal equation has a critical part. It's this one here. Well, the left part. I take X transpose X. That's easy. This product. But then I have to invert this product. And matrix inversion can lead to various problems, because not every matrix is invertible. So what can happen here is that this product X transpose X is singular or non-invertible. And there can be multiple reasons for that. One reason can be that I have too many features, that I have more features than elements or than samples. And this would be specifically a small sample size problem. I don't have enough samples. I have more features than samples, meaning more columns than rows. And if that's the case, this one here, X transpose X, is guaranteed to be singular. I will not be able to invert it. So now we see that we can have a small sample size problem in which we are not just training a model that is then maybe overfitting, but we're actually running into a situation where we have a matrix that is not trained, or we're running into this matrix product that is not invertible. So we are having a model that is actually not trainable at all. And there can be other reasons, even in a non-small sample size problem, where this matrix becomes singular. For example, if I have redundant features, concretely features that are linear dependent, for example, one column, so one feature could be the size of the house in feet, the other column could be the size in meter. This is just linearly dependent, and when you have columns in a matrix that are, or here in X, that are linearly dependent, then eventually this product will be singular as well. So it's not just small sample size problems, there can be other reasons for that. And now, how can we fix this? If we have too many features or linearly dependent features, we could just delete features and try to make this non-singular. One way how we can address this. But maybe I just have too many features and I don't know which ones to delete, and it's a real small sample size problem, so I maybe just don't know how to continue from here. Could be one issue. Then another solution could be calculating the pseudo-inverse. The pseudo-inverse is a different approach. The pseudo-inverse allows me to calculate the inverse of a matrix that is actually non-invertible. It's some sort of approximation of the inverse. There's a whole theory about calculating pseudo-inverses, and we could spend half of the semester on this. If you take a look at a linear algebra library, I'm just opening this maybe, and I'm doing a screen share about this. Just wait a second. We will, I'll do the screen share in a second. I'm just opening this. For example, in NumPy, we can take a look at that. In NumPy, you have in the linear algebra submodule the pseudo-inverse function, and it will calculate the pseudo-inverse of a matrix. How this can be done exactly, you can see in here, and there is also a reference to the paper or to one paper, while the pseudo-inverse is actually older than this reference here. And you can also take a look at the parameters and any assumptions you can make about this matrix. Like this, you can calculate the pseudo-inverse if you wish. So this is one approach how you can tackle this problem. There is another approach to our matrix from before, and it's actually doing regularization of our matrix X transpose X. And if we regularize it, we can also find or convert that singular matrix into a non-singular matrix, and then we're able to calculate its inverse. And I'll show you this now on my whiteboard. So this was just the intuition, very importantly, not a derivation. But what I said is we have our weight vector and we have our x transpose x, and we want to invert it, but it's maybe not invertible. So I need to regularize it. And the remaining part was x transpose times y. And how can I make this part now invertible? So it's not singular anymore. What I could do is I can add something on top. Concretely, I add a matrix on top, which is 1 in its diagonal, except the first element. About this, I'll say more in a moment. But the whole diagonal is 1, except that one element. And all the other elements are 0 in this matrix. And I can just add this matrix on top of x transpose x. And like this whole sum will be invertible, because if I add this identity matrix on top, I will definitely have something that is invertible, because the matrix will not have columns anymore that are linearly dependable, because I'm adding the identity matrix on top. Why do I have a 0 in the first element? Remember, this first feature was always 1, because we said that's just this 1 we multiply with the y-intercept, because we had I had this in the slides before, but I'll quickly go back so we're all on the same page. Because remember, my hypothesis was something like this. I said the weight vector times x, and concretely that's weight 0 times x0 plus weight 1, x1, and so forth. And I always assumed that this one here is 1, so I simply have my y-intercept here, and I can represent all of this as a product of the weight vector and the input vector. But this x0 and the y-intercept, they will not be contributing to this singularity, and I actually don't want to change the y-intercept, and that's why I'm putting a 0 here, and the rest of the diagonal are 1s, and all the other elements are 0. Like this, I make this matrix xtx non-singular, and I can invert it. But now the question is, how big are the values in x? And can I just add such a huge matrix on top? And what I can do is I can multiply this matrix with a regularization constant lambda. So it's a regularization constant. And this one, depending again on my specific problem, probably has somewhat large or probably somewhat small values. And then I don't interfere too much, because obviously I'm adding some noise on top. So it will impact my results, but it will make this matrix invertible. There are all sorts of other regularization techniques. Some regularization techniques do not add this diagonal matrix or near identity matrix on top. Some other regularization approaches address this xtx, and what it does is sometimes maybe just retaining the diagonal in here. So this could be one approach, retain diagonal. If I only retain the diagonal in xtx, xtx will be non-singular. I will be able to invert it. Again, this will lead probably to very poor results when I later multiply this with x transpose and y, but it's some other approach proposed in the literature. And there are all sorts of other regularization techniques for making the normal equation invertible. It's also written in my slide deck and well formatted in here. So this is what we just looked at. So, as a quick summary for today, we looked in this big data, small data, all data chapter. We looked at initially data quality. We looked at biases. And then we looked at small sample size problems. And this XTX and inverting is something you see in a whole family of other machine learning models, not just in a normal equation, but in other machine learning models as well. And this will certainly become singular for all these different causes, like small sample size problem, redundant features, not enough data, too many features, and all these constellations. And we have seen three approaches. Delete features, maybe not too great. Pseudo-inverse is one approach, which comes again with various pros and cons, or we use regularization. And if you want to use the pseudo-inverse, I've shown you where to find it in NumPy. And now you know how to make such a singular matrix invertible with all these different approaches. Next week, we will look, next week, in the next lecture. So today we had a double lecture. And I want you, since we use this to speed up a little bit, because today is officially still a lecture-free day on this Tuesday after Easter. So next week, we will not have a lecture. And next week, because I have a parallel appointment, and today we had this double lecture to speed up and have a head start. What I want you to do until the lecture in 2 weeks, so in 2 weeks we meet on campus again. What I also want you to do until in 2 weeks is to have a look at this MLOps chapter. For MLOps, you don't find a lot of slides in this slide deck. You wonder, first of all, what is MLOps? When you build a machine learning system and you run it on your laptop, that's nice. But when you want to deploy a service and run it reliably, you need to pay a lot of more attention to operations in how to run a machine learning system in production reliably. And that's a topic that has been called in the last few years MLOps. I personally don't like the term too much, I have to admit, because MLOps is, eventually just a special case of running a production environment reliably. But with machine learning, there are some new challenges because you also have to make sure your model stays up to date and a couple of other things. And because this is so well described in other sources, this is your homework to read it. Concretely, in Towards Data Science, I found 2 articles that describe MLOps quite well. If you go back to the beginning of the course, which is in which we discussed in the first week also literature, there's another book here. It's called Engineering MLOps. It appeared with Pact like 3 years ago. I think it's a very good book that also describes MLOps well. So your homework would be to read a little bit about MLOps, either look into this book or look into these two Towards Data Science articles and get a bit of an understanding. Do it until in 2 weeks, because in 2 weeks I will also say more about the seminar presentations. And for the seminar presentations and picking a design pattern, it's good if you have a little bit of an understanding of MLOps, because some design patterns also address MLOps. And then if you have any questions, let me know now about today or the course. Maybe just raise your hand in here. And if there are no more questions, we are done for today. And I'll see you in 2 weeks in class. And I'll send a round message in iLearn that we're not meeting next week because we had this double lecture today to already catch up. So see you in 2 weeks. Take care. Bye-bye.